All right, so good evening everyone and welcome to IHub Quantum Technology Foundation's first seminar of our FriQuant seminar series. And the IHub is basically aiming to create an ecosystem, a quantum ecosystem in the country, wherein there'll be collaborations between collaborators all over the world, nationally and internationally. And our FriQuant seminar series is one way of reaching out to maximum people, researchers in different parts of the world working on different aspects of quantum technologies and bringing them to students so that you know what's out there waiting for you to take on, the problems that are already waiting for you. So today we have Dr. Yeshpal Singh from University of Birmingham, and he already has a lot of knowledge in quantum technologies, a lot of years of expertise, and today he's going to specifically talk about highest precision outside labs, so atomic clocks and highest precision outside labs. So I would like to call upon Dr. Mahesh to formally introduce our speaker.
Dr. Yeshpal Singh is Associate Professor at the University of Birmingham, and he is the lead for precision timing and quantum clocks at the UK National QTF for sensing and timing. And he received his PhD from TIFR in the year 2004, and then he received European Marie Curie Fellowship in 2010, which led him to become a group leader for precision measurements and quantum simulation. He has a track record of over 40 publications in Science, Nature, PRL, etc., all high profile journals, and he has spoken at various international conferences, and he is quite rich, academically. So he is leading a portfolio of about 100 million. Let's not get into the precise number, it's already huge. And he says that the direct fund which belongs to his lab, direct fund, is about 15%, so that's about still 15 million pounds, so that's still a huge sum. So that's why I said academically he is quite rich. So currently he is leading several important projects, including at UK National QTF for sensing and timing, EU flagship project, and then many other IUK projects. Okay, with this introduction, I call upon Professor Yeshpal Singh for delivering this seminar.
First of all, thank you very much for kind introduction. Actually, it's I'm not very used to it because I am at home, and then it felt like introduction for whom. It's more like not like, it's literally my home. I know so many people, and not only know, but they are really really good friends to me, and I came actually to meet them, and so I also took this opportunity that to speak a bit about some aspects of the work that I have been leading in the UK or in my group. So I'll try to at least say a bit about it. So what I have chosen is highest precision outside labs. I thought like there are two aspects, and you will see very soon in following slides that there is another aspect which is very fundamental in nature. But I have chosen this one when I came to know that this is about innovation hub, and I thought like let me also pitch part of the work that I have been leading, which is related to innovation. And so I have chosen this is highest precision outside the lab, because the idea of at least quantum innovation is something that has been proven and tested in laboratories. Can we take it out? Can we make it field deployable? Can we use it in applications, either existing applications or unfolding new applications? And probably some of the applications we don't even know today what it might bring in near future or far future. So the talk is going to be more about metrology. Before I can speak sometimes a bit too long, so I thought like before really I proceed, I should at least introduce the people who actually do the work, and I am the one who normally just talks about it. So I have, these are the people who are, it's not the exact picture. There are some people either who have left 2-3 people from this one, but there are 4-5 others who have been added. So the work that I am primarily going to speak about belongs to Sarah, Vijay, Jonathan Jones, Marcus, Abhilash, and Alok Singh. So this is and also I should say Darren. So actually there is one person who graduated from here, Jitin. He is not in this picture because he was traveling to India to get married. So there was a good reason why somehow we missed him out in this picture. So it's so I have around I think 18-19 people in my group, and that's so it's a part of that work that I would be speaking today. So if you look at, like, one way to look at my lab or my group is really it's strontium and ytterbium. Ytterbium is yet to happen in a way. So we are making progress and setting up new experiment, but the experiment that we have been doing so far is based on strontium, and strontium is quite interesting element because it has got 2 electrons, and if you have 2 electrons then you can get singlet and triplet, and you will see in following slides. And so the energy structure in the atom is richer than if it was only 1 valence electron, and so that makes it quite interesting. And one of the transition you will see is very narrow as 1 millihertz, and that could serve as a very good purpose for referencing, and that's exactly what we are going to do when it comes to defining time. But for us, these strontium atoms, they are ultra cold. If people like me to really say a bit about ultra cold, how we reach it, I can say, but I have assumed in this talk that you can just assume these atoms are very cold, which means like 1 microkelvin at that level. So really ultra cold compared to room temperature, which is around 300 Kelvin. So for us it's really these are atoms with spins, spin up or spin down, trapped in a lattice. It could be 1D lattice. Most of the work that I am going to say confines to actually 1D lattice, but you can also have 2D lattice or 3D lattice, and that's what actually these systems are for us. So at the end of the day, I am an atomic physicist, let's put it this way, and then depending on what to sell, we put our sort of like mukhota or the face as an innovator or as a fundamental physicist or or quantum technologist, whatever it is. But at the end of the day, it's anatomic physics in optical lattices for us. That's what it is. And so using that one, the effect we are looking for, either we are looking for measuring time or setting off, let's say measuring gravity, then it becomes an atom interferometer, or measuring, let's say, magnetic field, then it becomes magnetometer. But at the end of the day, it's literally light atom interaction. That's what we play around with. So we manipulate atoms using light. Based on that one, the very first translational, so there are 2 ways to look at it. So one branch of the work that I lead is really out of lab. That's deployable, and you can say it's quantum technology and application oriented. And when it is something application oriented, which means it has to reduce in size, it has to reduce in power, it has to reduce literally in its weight, and it should be robust enough to take it around without sacrificing precision. So that's this theme here. When you have these ones, and especially because this is about innovation, and when you talk about innovation and applications, you also talk about really impact of it, and it's very difficult to achieve impact unless there are takers, and takers normally come from industry sector. Either they are already existing, you talk to them, or you really spin out an industry and take it to the market and make an impact in people's life. Okay, so that's one branch, and you could see that I'm involved with lot of actually industry from very small level to very big level, like as big as like 30 to 40 billion turnover per year. So these are you could see like BAE Systems or British Telecom. So these are really like from low, if you look at the supply chain from really lower end to far end of the food chain. So this is what we try to cover, and so that we have good cover to really see the impact of these devices, and that's what I'm going to talk about, this branch. Huh? You will see in the following slides. The second branch, which I'm not going to talk about today, as I said, it's more about innovation, is about really looking for fundamental aspects. And the fundamental aspects in our case is really looking at long range interactions between two strontium atoms, but long range here is dipole, and actually Regis is an expert in that one, so probably I'll be talking to him at some point about these things. And their idea is you can put them in 1D lattice, 2D lattice, 3D lattice, and then the interaction is so long that it can span over many lattice sites, like 10 to 12 lattice sites. And so it means if you have a 3D lattice, you can think of entangling 1000 atoms, for instance. So it becomes really proper many body physics that you can simulate, and then of course with that one you can simulate condensed matter physics or other aspects of fundamental physics. So this is roughly, I would say, that's how I look at this lab that we have here. In this case, it's not only with industry, but also we are interested to take this technology to space, and I'll give you some glimpse of that one. So just to motivate you that some of these things are already happening in a way, why time is so important and measuring it even more precise is so important. So if you look at it, this one, I do not know, I think if I click at it, yes, probably it will run. Does it run? Okay, it's not somehow happening, unfortunately. I think it's a typical of MacBook problem. So, but nevertheless, I think when we reach from one point to the other, today we depend so much on GPS or navigation system. We just place where I am and where I want to go, and then it shows like this is the path. This is the path we advise you to follow, and we often blindly follow that one. And there is, so what it is, that you have a lot of satellites, typically at the level of like 30 to 36 satellites hovering around the Earth, and then they keep sending signal on the Earth, and then you have this transponder, and using like 3 satellites, for instance, that can locate you using triangular location. So it's so in that sense navigation, and there is nothing, so it means this is time signal that comes from the satellite. So each of these satellites actually contains atomic clock, and if you make this clock even better, then the precision at which you could be located can be improved. So that's one aspect. The second aspect is like I don't know how many of you know, now all these SI units, like you have a kilogram, you have length, all these things, now they have been defined with respect to actually these fundamental constants. So this is a major change that has happened in last few years, last 2-3 years. And what is also a question is, are these, we have defined them with respect to these fundamental constants like Planck's constant, but how fundamental constants are really constants? Do they vary in time? So if you have a very good clock, really very precise, then you can put at least a limit at which you can say either it really varies or does not vary. And the best limit has been really put on these fundamental constants is really by atomic clocks, optical clocks. Then the second one, which could be quite interesting, especially in Pune, we have IUCA and NCRA. So there is what you can do is you can effectively increase the synthetic aperture of a telescope. So even if these telescope antenna, they are far away from each other. When I say far away, it's not 1 meter, 2 meter. These are like hundreds of kilometers, sometimes from one continent to the other continent. And you can't, one way is of course you can make this antenna as big as possible and you can collect more light, but once you have defined, for instance, which star or what object in the space you are looking at least the wavelength is very well defined, but there is a technical limit how big you can make this antenna. But what you can do is you can coordinate all these antenna by anatomic clock, by precise clocks, and increase the synthetic aperture. And when you increase the synthetic aperture, your resolution goes manifold. And that's what actually today's astronomy antenna, which astronomy telescopes actually have been working, because each of these antenna is supported by hydrogen measure typically today. And that's already very, very precise. So if we have better clock, we can possibly do better there as well. So we can form long baseline interferometry it is called. Now there is also another one is long baseline atom interferometry, where people are looking at really detecting gravitational waves using these cold atom technologies. The fourth one is, a lot of geophysics people, their job is really to understand physics, like the movement underneath, or even to define the height. There is no uniform actually defining height coordinate system, global coordinate system today, because each country has different reference, and typically it is sea level many times, and geometric height is not good enough, which you can use probably from GPS and other satellites. So there is a lot of error. When I say error, between two, let's say for instance between if I talk about Europe, for instance, between France and Germany, the difference could be easily 10 to 20 centimeter. Between Florida, that's quite stark actually, between Florida and Toronto, it's 70 centimeter. Can you imagine? So there is a need to have a better global height system, and that can be done if you have very good clock. So you can measure the gravitational potential, and that can become your global reference. And so geophysics people are very excited, and because these clocks have reached that level where you can confine geo within 1 centimeter, so the error could be also confined to within a centimeter, and that's quite remarkable. Yeah, this is it's a I think it mainly comes from this high energy physics people and the standard model, and so they try to show this impact of these things and how the but it may not be related to mu, but they connect it to other quantities in a standard model. That's my understanding of it. So this is so what I wanted to say, they are very useful from fundamental physics to really very applied and including day-to-day life. Yes, to some extent, yes. So like gravity does couple to clock, but how much does it couple to that? If there is no coupling, we can't measure this fundamental concept. That's the first thing. So just I wanted to give, which I find quite good example. This is one of actually my favorite pictures. So there was this recently, when I say recent, I think it was 2-3 years ago. There was this black hole image was constructed, with the data which was taken over a long time. And if you look at these antenna, these actually what is called now event horizon arrays, it's just acted as a single telescope. You see the distances are intercontinental, and it acted as a single antenna, which I was talking about. And if there was no atomic clock available, I'm not sure we would have been able to really do it. So this is, you see, it's also make things much more interdisciplinary and much more attractive. So I just wanted to give you a picture that it's not only that we do it because someone likes to measure precise time and has gone crazy, but the impact you could see in fundamental physics itself and our understanding of the universe. Okay, so what I wanted to, I think this is enough for motivation or introduction, but I wanted to say the Quantum Hub I have been part of, and I lead this activity within this Quantum Hub. I wanted to give a little introduction to that one. This is UK Quantum Sensing and Timing Hub. It's a big project. It has got more than 150 million really investment in it, when I say mostly from government, and lot of collaborative projects, more than 100 collaborative projects. It has started to create jobs in industry, because these politicians, and this is where she is trying to do, I think, and you need to get patent, and these are the numbers people like to see, especially the government authority or somebody who writes check. So this is kind of like summary what has come out of it, and if you look at it, Birmingham is somewhere here, and it really interacts and also collaborate, engages with lot of partners, over almost entire UK. So it's in that sense it's a big activity. It's quite national level in its character. So there are what it focuses on. So this has like these are the main ticket items that it try to focus on. What I'm going to talk about is time, or I have been talking about is this time 500 meter. This 500 million. M is for million here. That it can generate that level of impact. Gravity, yeah. Then it's gravity gradient, magnetic fields, rotation sensor, terahertz, and it's quantum light, which means instead of manipulating atoms using light, you manipulate light. You might have to use atoms to manipulate that light, of course, but in this one you manipulate light. You use the quantum property of light there, and it builds on the ecosystem and supply chain and these big companies, and that's how you generate that sort of impact. So it's a quite big exercise, and these numbers of course are not really very accurate. These are more educated guesses. We had written a roadmap, a big roadmap, and that's how these numbers have been generated. Yes, it's also, it's not India in that sense. I feel a bit pity, to be frank, but for them, farming, they represent it by cow, and they need to identify which cow is where, and so they have some sort of a device attached to each cow, and also using magnetic field, for instance, you can do certain level of health inspection in these animals, and if you know well in advance that this cow is not healthy, at least you can take precaution. So that's where these numbers come from. So the idea is that it goes across from animals to really human beings, mapping brain imaging, for instance, mapping human brain. That's one of the biggest activities actually in this hub, and it has a huge impact in the health sector. So if you see, this is including actually heart magnetic tomography you can do using that one. So this is again what it builds on. Okay, so this is that's what I have been talking. Oh, sorry, it's a bit slow. I hope it will go back. So I just wanted to give you a little bit, like when I say atomic clocks, or when we say just precise clocks, there are actually two, typically at least in this community. If you say atomic clocks, these are typically microwave, in the sense you still use atoms, but you use levels which fall in microwave region, like gigahertz for instance at most. So these are atomic clocks which you could see that they were the ones which were realized earlier than optical clocks. So the second branch is optical clocks, where you use actually optical transition in an atom to define time, and that's why you could see these two colors. So red ones are optical clocks, which means you use optical transition in an atom or an ion, or you use atomic level which is in microwave domain, which is called atomic clock. So if you say to someone atomic clock, that's what at least this community would understand, this blue one. If you say optical, then that's what they will understand. And quantum could be anything. I think quantum is a bit more fancy word today, because it sells well. When you say quantum, anything quantum, it's kind of buzzword. Okay. But the point I wanted to say, if you sorry. Yeah, it is intentional, because this is the leading clock today. It has gone into -19 uncertainty, while all the atomic clocks are actually 1 part 10 to the power -18 in terms of uncertainty. In terms of stability, of course, they have also gone into 19, but because this is uncertainty. So what point I wanted to say is that if you look at the slope, is actually more in favor of optical clock. So if you want to build higher precision, higher accuracy, then the optical clock is the flavor of time. This is what I wanted to, and this is where we are in terms of the best accuracy. It's 9 times 10 to the power -19, in fact, is the best accuracy based on aluminum ion clock today. So I have not yet said what this really clock normally in terms of cartoon. So I have prepared this cartoon here, what an optical clock really look like in terms of if you have to build a cartoon. So you need, as I said, it's optical transition, so you need atoms. So you need actually three fundamental things to build a clock. You need an oscillator, which means like if you look at really wall pendulum, like these wall clocks, you had this pendulum going back and forth. So that was your tick for time. Here you have a laser that beats much faster, of course, 10 to the power 14 to 10 to the power 15 times per second, and that's actually your flywheel. So that becomes your pendulum. You also need a reference, because it can just give you a time, but what is that time really? Is it 12 o'clock or is it 1 o'clock? So you need a reference, and the reference, and also it could drift with time. So you need to really discipline it, and that's where the atoms come in. So they act as a reference, and then you need to count those ticks. Like in a wall pendulum, you can count very quickly, like 1, 2, 3, 4, and you can use electronics, they are very slow. While these are 10 to the power 14 to 10 to the power 15, there is no electronics actually that can count that type of ticks in a given time. So what you need is an interface between your electronics that's available or that you can do, which can do jobs typically in gigahertz, up to gigahertz, like 10 gigahertz or that level. But you need a gear, and that's where the frequency COM comes in. So it interfaces between this laser and the application, which is typically as 10 megahertz or 100 megahertz, and so it becomes more like a gear that you can go from higher frequency to lower frequency, which is more of your use with the same stability currently. And so you have these three elements, and so initially normally in optical clocks what you do is this laser is stabilized against a high finesse cavity. When I say high finesse, is typically, which means these are as high as like 300 to 400,000, which means the light, before it can get lost, if you have a photon, it jumps back and forth between these two mirrors 300 to 400 times before it can be lost on average. And so that's the finesse by and large, that's how it is defined. And so you pre-stabilize it, because this transition, as I said, is of the order of 1 millihertz, and so you need to have very, very precise your laser frequency. So it has to be very narrow, and then once it is stabilized to these atoms, you have been able to excite this transition, then you can give this feedback loop, which is typically slow. Atoms react slowly, and then you can, in long term, you can stabilize, and that's your actually clock. This is specifically for strontium, because this is where we have been working on. So you have so we use laser cooling to reach this 1 microkelvin or so, as I said. So in strontium specifically, you see, as I said, it's a 2 electron system in valence energy state, and because of that one you have a singlet state. You could see this is singlet structure, and that is actually very good. So we primarily cool, which we call first stage cooling at this transition. It's very broad, around 30 megahertz at 460 nanometer. Once you are able to cool these atoms at that one, but they are cooled to something like 1 millikelvin, so we consider them very hot still. And these are real pictures of atoms. So that's what actually you see when you take a picture using a camera, and you can see with naked eyes as well, because naked eyes themselves are very sensitive to this wavelength 461. And then once you have cooled them to millikelvin, then you transfer these atoms to this transition with 689, which is actually around 7.5 kilohertz. The advantage is that you can reach to, in principle, even 100 nanokelvin at this transition. Typically 1 microkelvin is quite common, or 2 microkelvin. And then what you can, but the price you have to pay, because this is so narrow that you are not able to accommodate all the atoms you are able to trap in your first stage cooling. So you normally broaden and then you decrease it. And so typically in the end, what you started with, let's say of the order of few million atoms, you end up roughly 25% of that one, 1/4 of atoms that you can use for your clock business for second stage cooling, for instance. Then this is where we are. This is the, as I said, first stage cooling stage. You can add some G-man slower, but I am not going to talk about it. It's also part of first stage cooling, I think, just to keep things simple. And then you can go to second stage cooling. As I said, first you broaden the transition to capture all the atoms here, and then you narrow it down. So it's actually, that's why it seems 2 stages in second stage cooling. And then finally what you do you trap them in lattice, because now they are cold enough, and now you can form optical lattice. Optical lattice means if you have one laser beam from this direction, another laser beam from this direction, and you interfere these two beams, what you will see regions of minima and regions of maxima in intensity. And if the laser is actually radio-tuned to the transition you are interested in, radio-tuned in the sense it has less frequency than the transition to excite that particular transition, then it can attract the atom using dipole force at maximum of intensity, and that is exactly what we do. So, you could feel like as if these are harmonic oscillators, and you have like this ground state here trapped, and then the excited state, this one in the excited state of this optical lattice. And there is this idea of magic lattice that we apply here. There is a real 813.4 nanometer for strontium, and that is called magic wavelength in the sense because this is the transition 698, which is your clock transition, which I said 1 millihertz, that is your reference level. So, what it does is it affects this level the same way it affects this level. So, the transition frequency remain intact, and that is what the magic wavelength is. So, now you can do spectroscopy because you have been able to trap these atoms, which means there is no motion anymore this one. So, you do not have any Doppler shift, and so you are very close to real transition in an atom. So, which means you are really a reference which is kind of universal reference, because these atoms are the same if they are here or on a moon or any other continent, and nature has made it for you. So, there is no really I would say defect from one atom to the other, as long as of course your environment remains the same. It does not affect that atom. So, that is what actually an optical clock is. The next one. So, that is what these are the phases we go through. So, if you look at there are now we have now built the ground essentially what an optical clock, how we can go around. Now, you have two pathways. So, one pathway is that you do not care about how much power it requires, you do not care about how much space it requires, you do not care about how much manpower it requires to operate this particular experiment, but what you are interested in, I want to build one of the best or the best clock ever, and that is one branch, and that is what a lot of people have been doing, like people at Jila or people at NIST or in Japan. And they have been able to, as I said, I showed some time ago that you have been able, they have been able to demonstrate up to 10 to the power minus 19 level of stability and accuracy. So, that's great, and you can do a lot of fundamental things, but the price you have to pay, you are confined to your lab, you can't take it out, and it's quite complex. Okay. The another pathway which we have taken is which is size, weight and power, which means you work on these parameters, size, you reduce the size, you reduce its weight, you reduce it's also in fact what is also added often C, which means you make also cheaper, especially for marketing, but this is not being an academic is not primary thing, though it is a consideration. So, you do it size, weight and power, but then it should be at the not at the cost of really you sacrifice your precision, not at least a level that you would like to have, which means let us say at the level of minus 17 10 to the power minus 17, which is many orders of magnitude better than what is available today commercially. So, you can take this vertical path, it is a bit more challenging that how you, so the real challenge is how you reconcile technological or innovation advancement without sacrificing really precision and accuracy, and that is the path we have taken. So, if you look at it, like we built in our group one clock which was arguably the first transportable clock in which was in European consortium, and that was around 1000 liter in size, and with the precision today it ticks at 3 past 10 to the power minus 18, literally in terms of transportable one in Europe, this is the best one. But then we became even more ambitious, let us reduce the size and weight by factor 10, like one order of magnitude more, but without sacrificing the precision which is 10 to the power minus 17 at least. So this is the journey we have embarked on. There are other people, of course, who have joined after this clock, which is itself like German Standard Institute, PTB, China. Again, they have in PTB another clock they are embarking, and Toptica, which is called actually OptiClock. This is German Quantum Technology Initiative. So now it's a big fashion even to embark on this one. So all the competitive groups nowadays or national initiatives actually focus quite a lot on this branch of the I would say research or innovation, if you like to call, and that's where the innovation is. And more science is, of course, in this side based on highest possible precision.
American efforts for the transportable or mobile clocks?
Sorry?
Are there any American efforts?
Oh yeah, as I said, in NIST they are building one. It's not yet reported properly, but I know they are building one based on ytterbium. There are two initiatives, one by JPL, that's based on iron, but less in precision. There is another one in NIST, which is based on ytterbium neutral atom. And that's similar to our approach in that sense, but it's it has not yet been published. I think they are still in making.
JPL is probably mercury ion, right?
Yes, it was mercury ion they started with.
They are doing mercury or
I think they are also working on strontium now. Yeah, but they might also change to iron, because these things are not reported unless you have a direct connection or somebody speaks to you personally. So in Birmingham, like in our group, we have three these systems. As I said, so this is Quantum Technology Initiative across Europe. So their idea is to make a transportable with 10 to the power minus 16, but it should be applied to a communication network with British Telecom, as I said. So it has a specific application in mind, and we have been working together with them. We don't mind if it is like 1000 liter, but it should be robust enough and transportable. The another one, as I showed, we did it in some time ago in 2016, and in 2018 we were able to get 3 past 10 to the power minus 18 stability for it. And then we have embarked on for some time now to reduce the form factor by 10, as I said, mini clock. So these are the three systems. Of course, we have more assets in Birmingham, which is typically not found so easily. So we have got 5 frequency comms. Out of these 5, actually 4 are transportable, 2 are literally portable, and 2 are transportable, and 1 is optical bench based. And then we have also got 1 active hydrogen measure, which provides a good reference to a lot of other reference things where we want to narrow down our line width, for instance, to 1 hertz, that we can easily do via frequency comm, or we just want to make a measurement against against hydrogen measure, that also we can do. And then we have also built together with Kronos, thanks to them, 10 to the power minus 14 stability. This can be referenced to UTC, so which means we can be an accurate we can have an accurate time in our lab which is within 3 nanosecond of the UTC time, and that's how, which is globally defined, because UTC means universally coordinated time. It's a French word, that's why you see not UCT but UTC. T is for temps there in French. And so it's so this is these are the assets I wanted to show in Birmingham in this regard. So as I said, this is space optical clock one we transported the setup 2015 to German Standard Institute Technology, and then if you look at it, this has reached 3 past 10 to the power minus 18. So these are measurements, and in terms of uncertainty is 2 past 10 to the power minus 17. So it's one of the best clocks in uncertainty in Europe, and the best clock in terms of the stability. Okay, I think what I want to cover, let me see. Of course, we have, as I said, we have some ambition in space, and we have been working in European consortium to reduce the form factor and robustness, where you are not there really to tweak it. Everything is remote, and so whatever you sent it, you just have to forget in a way, that you can't just go and correct it. So it has to, one has to look at lot of other things and reduce the form factor. So the target is 1 part 10 to the power minus 17, and instability somewhere 1 part 10 to the power minus 15 per square root of tau, which means in 100 seconds it should be minus 16, in 10,000 seconds to minus 17. So that's and you could see it's a lot of design has already taken place. I'm not showing all of you, but I just wanted to give glimpse that there is a huge interest to take this technology also in space, because there's a lot of applications there, fundamental as well as technological. So that's project is called ISOC, that's going on together with ESA. So what I wanted to say here, in space optical clock, which is actually the first, arguably first transportable clock with one of the highest precisions today and the highest in Europe in that sense. If you look at it, the size where their atoms are trapped and manipulated, which is the heart of a clock, and that's what is done here, for instance. But in addition to that one, to cool them, to trap them, you still need some more things, like this is atom source, then you have a Siemens flower which helps you to pre-cool atoms before you get into your first stage, and then you trap them, cool them, and do this spectroscopy to get the timing information in that sense. So you see, it's a big thing. It's more like 99 centimeter to be precise, but you could see this breadboard like 1 meter, 45 centimeter, 60 centimeter. So it's a reasonably big, but in this field it's actually one of the most compact, just to give you the scale. So what happens? I think the idea is, can we make it even smaller than, and the idea is, can we get rid of the Siemens load, which is around 30 centimeter in this case, and can we also get rid of these pumps, like these are one of the unnecessary, or we need to create ultra high vacuum, but can we get this ultra high vacuum without having too many pumps, just having, let's say, 1 pump? Can we reduce things more towards here? That's where everything is happening in the end. So answer is yes. So this is where the second project comes into picture. So this is mini clock. If you look at it, compared to that one, this has been reduced to now around 60 centimeter, coming down from 1 meter to 60 centimeter. So roughly, you have got substantial change, and instead of like this height remains something similar, but this has also become this height also become much smaller. So if you look at what is the state, at least in neutral atoms, including in fact ion atoms in transportability. So if you look at just this part, atomic package like this, which has been shown here, where atoms are trapped, manipulated, cooled, done everything, this work, this particular one is this blue. You see, it's hardly visible. Of course you need lasers, etc., and that takes most of its space here. The second one, which is a Chinese calcium ion clock, I think. So if you look at its atomic package, it's actually much bigger. Overall, putting together lasers, because it's slightly different element, but you see it's not very far from our one. So we are very close in that sense, and atomic package is much smaller, and any other clock you see is many times more than what we have been able to reduce this one. And we have been able to demonstrate that you can have a lattice trap time of the order of half a second, which is this is what we are looking for in transportable clock. So it fulfills those basic parameters, which is much smaller. You have a reasonably long lifetime in lattice, and it's robust enough, and it was taken actually between 2-3 cities in a car, back and forth. It not only survived, but as soon as we plugged the wires, it was running immediately. So everything we were able to do in 1.5 hours, which for this system, complex system, is quite remarkable. So this is I would say at the moment is the state of the art in optical lattice clocks in terms of taking it out. There is one example I can say, I did mention it, but if I wasn't clear, there is an initiative in Japan. He has been able to build 2 clocks and able to do measurement over 400 meter, because he has a tower, and he has that precision. Is actually the best transportable clock, but the volume is of the order of 1 liter, so which means 1000 liters, sorry. So which is much bigger than this one. You could see that's what Recon Lab. You see this is blue one line compared to this one is much bigger, but then he has been able to demonstrate this is 10 to the power minus 19 that it ticks. So that's a quite remarkable achievement, I must say. So this is then the question was, as I said, let me just take this light again. The question is like, now we have been able to reduce, like got rid of Siemens lower, can we just confine ourselves to this chamber? and that's the journey we have embarked. So we found that we can generate a novel source, and you could see that this is the chamber, this is the only chamber, and it is evacuated of course, and you put strontium oxide in the same chamber, and if you use laser and you really shine onto this one, what you can do is you can generate strontium vapors for to be trapped, and if you look at the velocity distribution is around 0. And just to give you an idea, something that you can trap is the velocity you are able to trap is not more than 50 meter per second per centimeter. So if you go either side of 0, you are able to substantially capture the atoms which are generated, because this is around 0. If you compare it to thermal source that typically people use, if you look at this profile, that you see if you are 50 meter per second, you are somewhere here, and most of your atoms are not being used at all. And not only that, because it's thermal, it takes time to switch it on to make it work, and then switch it off, it is still radiating, while because this laser you can do it very fast. Another important thing that came out, people thought, the strontium has very low pressure, so it goes and hit the wall and it just sticks there. We found actually it does happen, but it happens after it has gone through at least some collision, because we found this temperature or average temperature of the distribution is around 390 Kelvin. So if you look at it, it means it is Gaussian. As many atoms are going from this side to that side, as many from this side to that side. So it's a thermalized sample that you get that is there to be trapped, and so this is quite promising in that sense. So it means you can get rid of, there's a further possibility you can really shrink your setup even to much smaller form factor. So you might say in strontium, just to let you know, typical is strontium 87, which is fermion, because two fermions don't sit together. So you can get rid of really fundamental problem of collisions while bosons stick together, and that can limit your stability and accuracy of your clock. So people prefer strontium 87, but it has got abundance of 7%. Is it good enough for that one or not, this source? And we found actually it's good enough, because you can still trap 1 million atoms, which is typically good enough for a transportable clock. Of course you trap many more atoms in strontium 88, because it has got much higher, roughly 10%, 10 times more percentage, and you could see that this can be done. People tried in Japan following us, that it also works for ytterbium, if someone is interested. So I think I have taken quite a lot of time, but I would take literally not more than 5 more minutes. What I wanted to show is an application that this precision, some of the application, this is together, as I said, this is interdisciplinary, is together with the electrical engineering department at the University of Birmingham and National Physical Laboratory, their team there, and we have got 2 PhD students, and we are looking for 3, but when we find some suitable one, of course that person can join the team. So what I wanted to show, that it actually is of really relevance for day-to-day life. Somebody was talking about air taxis and other things. So if you look at it, the idea is of radar, and so radar is nothing but a timing device. So what you do in a typical radar, you fire a pulse, let's say this is your object, you fire a pulse and it returns from that object and you receive that pulse. Depending on how far it is, if you measure the time difference, you know how far it is, and because if it is moving, it also Doppler shift your signal, and you also know its velocity. So you know these coordinates, and that's how typically a radar works. The better stability of your timing device, which is at the heart of radar, you have, the better measurement you can do, and this is particularly the case if you look at the phase part of it. I just want to give this one why it is so important, is if you look at, let's say these are your signals, because you have got birds flying around, you have got small drones flying around, which has become quite common nowadays, and you have also trees, and with the air that you have these leaves flopping back and forth, and then you have also normal aeroplanes, for instance. So you have got very congested environment. I am not talking about contested, that is also of course one application, but at least the congested environment. And if you look at, this is your thermal noise, and if it is an ideal oscillator, all these signals can be seen, which means you are able to identify drone, birds, and like aeroplanes, these are these signals. But if your oscillator, which typically the case, if your oscillator is not that bad, which is being used as a timing device in your radar, then you see you start to get the phase noise, limited signal to noise ratio. And if it gets even worse in the sense that the other and your environment start to become more congested, and you see that is in fact phase noise start to add, the clutter signal start to add, and you start to lose some of these signals, especially coming from smaller objects, because your cross section is much smaller, and you see that some of them you have almost lost, and especially closer you are to your zero frequency, which means the slower moving these objects, the smaller these objects, you start to lose them out of your screen before you can detect them. And so that's the application we have found and we have been working, and if you look at quantum, you start to see these objects again, even if you have very congested environment where you can still operate and you can identify different things. Geophysics people are also, geography people are also quite interested, because they want to specify, they want to do this bird specifications, which species and from where to where their migration, and radar is one of the probes they use. So I wanted to just say that we have installed 2 radars which are roughly 200 meters apart, and that you can use them as a single radar or in a network. And then the idea is, I would just be quickly, that if you do not have very good clock, you can get false signal, and if your clock drifts, which is very very small, 2.5 millihertz per second, that can come to your screen as if the object is moving like 30 meters per second, which is typical speed of today's drone. So you might get false alarm, which is not good. So you need much better clock. That's the configuration we have been working. So you have these 2 radar. On the 3rd node of the triangle, we have our lab, and they are fiber, phase stabilized fiber connected, and then we can do this synchronization or single radar enabled by quantum oscillator. I think I should really stop here. I am happy to answer the questions if there are more things I could say, but I think I can see I have already exhausted a lot of my time. Thank you very much. Okay, yeah.
When you talked about the antennas in observatories like GMRT have, so there you said some of these clocks are used. So which ones precisely? I mean, those are clocks built by your group?
No, they are today they are not built by any group. In fact, they are using hydrogen measure, which are commercially available, but they are hydrogen measures, yes. But there is a talk, if you want to make even better timing, stamping, and even more precise, then these clocks will start to use once they become, of course, available. The cost becomes one of the factors, of course. So one of
Do you have anything which is commercial, which is made commercial?
Not yet, not at this level. There are clocks, but they are at much smaller scale, in the sense 10 to the power minus 10. These are CSEC, or are called CSECs. These you can say it says cesium atomic clocks. There are also rubidium one, compact clocks, but their stability is minus 10. You see, even GPS is minus 13, 3 orders of magnitude, but they are very small. So for certain applications, that's good enough and cheap. But if you want to do some of the applications I have highlighted, then you need much better timing, which is not yet available. Commercially, I mean, in labs, yes, but then they are not yet deployable, and that's where all the focus is, to deploy them.
What is the approximate cost of this one model?
Which one? You mean radar or?
Portable, yeah.
Okay, clock, I think these are expensive kits. At the moment, I think they are more in the niche one, because we are not selling them, and there is no company yet selling. They are still, these are, you could see, these are research groups together with industry sector, trying to explore these ones, taking them out of the lab. That's where we are today.
But what's the cost?
Project cost.
Okay, project cost typically, I think, like for instance, European Quantum Technology Initiative is 10 million. Okay, but let's say one clock, I don't think today, if you want to, please don't quote me anywhere, I'm being recorded, but I don't think it's going to be less than, let's say, 2 million or few million pounds, because this is not yet in the, once it goes in production line, and it is you start to scale it up in the mass production, then of course everything start to come down. So you could assume factor 10 at some point, but they are still going to be expensive units, not going to be like 5,000 or 2,000 in terms of pounds. There will still be maybe, you know, if you have good pocket, then you can afford, or somebody gives you. Yeah, but this is where the drive is today, at least in terms of the clocks. There are a lot of other things, but one could say it's atom interferometry, like gravitational wave is another drive. Why this clock technology is so important there is all clock technology people are looking at today in terms of the atomic detection of gravitational waves, particularly in low frequency domain like 1 millihertz or less than 1 hertz. That is where interferometers in those certain range can detect certain gravitational wave sources. So there is a project called AI, and I am also part of that one, but again it is a national level project.
You spoke about moving from microwave clock to visible light clock. Visible light clock is more accurate, more precise, right?
Yes.
And do you foresee moving to further up, like UV?
People have been talking about, there are some groups, for instance at PGB, German Standard Institute, and other places. They have been looking at actually nuclear, and also in Japan, nuclear transition. But they have yet to find that transition first, that is the first thing. So in principle, yes, if you find it, if you have technology available, then of course there could be certain, but I have my own apprehensions on it, because there are many other factors. And I have seen like one example, just to give you a bit an idea, is like mercury clock that was set up in Paris in France, and that is almost as good, and that is good for certain one, like black body radiation is one of the issues in optical clocks, and that is very good for this black body radiation point of view. That has very small component of that one, but their wavelengths to operate is in UV, like 200 nanometer or that sort of things, and when you have to change your crystal almost every week, and even dust can create problem, you are more maintaining the system than really operating it. So it has demonstrated it, but the technology yet not there in terms of that. It's an interesting thing in a lab, but probably not so much for deployability, not now. So those effects, like for nuclear physics, it's similar. When they have the transition, they're looking for 7 electron volt, so which means you have 7 times more stability in principle going by the same standard. But then you have many other effects, which means like you are already in X-rays kind of, so.
Aluminium ion is also UV.
Yeah, aluminium is also UV. Yes, this is true.
The point is, by going to UV, you can probably gain by factor of 2 or maximum.
Yeah, but
the point is going by orders of magnitude, and that nuclear clock probably can do at some point.
yeah, but there are others. You have a crystal, and how do you? They have not yet found transition. So there are something. So you could see there are a lot of challenges apart from. And then when you have something in X-rays, is it coherent radiation you generate? So all these things, while laser is coherent by its own nature, and you can stabilize. So there are certain technological things which are more in favor of optical clocks, like normal optical clocks. And ion is another favorable one, where you can make it transportable one or portable one, relatively easier than atom one, but then you have just typically one ion, and so it takes much longer time to reach the same stability or accuracy than if you have an atomic neutral atom base, where you get easily few thousand atoms and you very quickly reach that stability, like in in a second. Probably that would take many 100 times or 1,000 times more time, but they are also useful for certain things, of course. So those yeah, it also depends what you are trained in, of course.
So at the beginning of your talk, you mentioned you have used exclusively multi-line. Is it to keep things compact because you need only
No, because atoms are being used as a reference, because your laser is your flywheel, that's giving you the time, but where it is running, that is defined by that transition, and that transition can be impacted by magnetic field, for instance, can be impacted by just atoms have thermal motion, because as I said, it's 1 microkelvin, for instance, but still they are moving. So what you do is you try to reduce those effects, and one of the things that's common is this Doppler one, that they are moving thermally, and what you do is you tightly confine them, and so that you take away this Doppler shift, and so that's actually, that's more to confine them in a rigid way than really to make the compact, because in fact it makes it bigger, because you come up with a laser and then you also have to have optics to insert it.
It doesn't matter whether it's 2D or 1D, you just need to keep them.
I think no, 1D is already demonstrated, you can reach really high stability -18, where a lot of these applications are already, you know, what you require is already, as I said, commercial, let's say GPS -13 available, and these are minus, so which is roughly, you know, 100,000 times better, these clocks, than what GPS has, for instance. So in that sense you can already gain a lot of things probably you don't even require, like for our IQ clock, which is European technology initiative, European wide, we have targeted only 1 part 10 to the power -16, because a lot of things that we can do in communication sector compared to what they use today are already good enough, you know. So you can always go, so 3D, for 2D doesn't make much sense in clocks, because it's more the gravity against which you need to trap the atoms. If it is 2D, let's say in this direction, it will just come out of that lattice very quickly, while the lattice is always typically along the strong axis of gravity. If it is 3D lattice, then it becomes more interesting, in the sense, because now you can have many more atoms without interaction, because even in this 1D, I have not talked about it, at -18, this dipole-dipole interaction start to become important, not S-wave collision but P-wave collision, even in fermions. But then building 3D lattice is, so you can do it in lab, people have done it, but then you are moving away from your target, really something that you want to explore in applications, rather than you want the best clock. So that's where I think one needs to make a decision.
But for fermions you have spin-spin interaction,
Yes.
and that plays any shifting of the clock transitions?
Sorry?
That shifts the clock transition?
That's a P-wave, like Junior has published that paper some time ago.
Spin. P-wave is just atom-atom collision. I am not talking about atom-atom collision.
No, I am not talking about atom-atom collision, I am talking about spin is P-wave. So S-wave collision is absent in fermion, but P-wave collision is there. So like typically in 1D, we talk about, let's say, 1000 atoms, and typically filling per lattice site is many times less than 1 on average atoms per lattice site. So there is no atom-atom collision as such, you know. But when you go to very high precision, then the other wave, like when you have partial wave expansion of your wave function, that they start to contribute, of course, at much higher level. That's what I said, if you are really keen, I want to get the best clock, then these effects start to become important, collisions with background start to become important, what's your vacuum, what's your background, and people have done some of these things, especially in NIST or GILA, but then, you know, you are more interested in the best clock possibly you can build and take out these effects you can characterize. While in our group, at least, we are not interested in that, we are interested in deployability, is it good enough for this given application, we are interested more in application driven by, you know, application driven figure of merits, rather than have the best clock and then we see what do we do with this now, you know. That has been our drive, at least, that we are more interested. That's why we are interested in space, we are interested in telecommunication, we are interested in radar applications, because radar is an interesting case in the sense, because these are classical radar, so which means the industry doesn't have to be replaced. It's only the oscillator that actually operates inside radar needs to be, you know, replaced. So all your infrastructure you can take advantage, and the market you have built, and you can still, it might be a bit more costly, but radar themselves not always so cheap. So it does not really kind of, specifically for a lot of application where people are looking at drone detection in a contested environment, you see, this is a reality, it's a hardcore reality. Typically for these type of applications, defense is one of the early adopters anywhere. So these are the guys probably would be more interested. They don't care about how much it costs, does it serve my purpose or not. That's the most important thing that defines their goal. So some of them might be interested, but even in civilian, like these drone things, pizza delivery, you have now birds and you have these tall buildings, how you navigate through it. Even in autonomous car, that's another application which might come in, which would have like 20 radars in it. It's not only like you have to differentiate between a pole and a walking person. Also you have to see which environment you are. So which means like you also have to be aware of your environment, situational awareness. That's the word typically used for it. So which means like what is the other car, what speed it's moving, what space available to me, and it's and this interference, etc. So this phase coherent detection can become quite defining things. People are also doing, of course, LiDAR has similar application like that one, but not exactly the radar applications we are interested, because then you have to change the entire infrastructure. There is no oscillator in LiDAR as such. So these are the things. You have platform, and you need to equip your platform with different sensor, and that's where I think the quantum technology is pushing things. Even if you have quantum computer, you still need sensors. Where is the data coming from? Okay, just quantum computer, you might simulate big molecules, and in medicine that's one of the examples people cite. But in real hardcore applications in field deployment, you still need sensors, in your platform. So I think this is why sensing is quite key and complements a lot of other things like QKD, quantum simulation or quantum computation. Quantum simulation is temporary stopover in my view again. So yeah.
Yeshpal, for your space application now, so what kind of energy cost are you looking at? Because if you send it up, you will need to.
Yeah, space is especially it's costly, because when you talk about space, if you want to do real mission, then you are talking about of the order of 100 million. It could be multiple of that.
The financial cost. I'm talking about the energy cost. How much energy will it require to keep that?
Like what we are, yes. Not always. Like International Space Station, you can have other generators in principle, because even human are there. But in a real satellite, which could be probably in future, this is so we are looking at of the order at the moment of the order of 100 watt, and that sort of energy scale is actually approachable. And that's where these things start to become important. So that's where I said the figures you start to speak in, typically that's the language we started to learn when we talk to application people, especially end users, whosoever that it is what is its size, what is its weight, what is its swap, which means size, weight and power, and then of course how cheap if I want to sell it.
Are you also trying to working on miniaturizing the optics part, because that actually
That is so we are not looking at, of course, if you look at the optics evolution itself in the market, actually is miniaturized quite a lot. So Newport, even the mirrors are much smaller than I used to see 5 years ago, for instance.
how about the lasers or CAD?
Oh yes, it is there. In Hub, I haven't spoken, I have only shown one window. There is a parallel one, and I am also involved. We are developing VCSEL lasers together with Strathclyde University. These are semiconductor disc laser, which can provide you much higher power, much narrower bandwidth, and so it means something that you require this big laser. Idea is, can you do with a diode, and where you can do with the diode, can you put things on a wafer, like you have a laser diode on the wafer itself, then you have isolator on the wafer itself, modulator on the wafer itself. Typically for telecom technology, this is doable. Integrated optics. So that idea is there. Yes, that's also happening. Then you have, instead of this frequency comma I have in my group, the smallest is this big 19-inch rack and this height. That's the smallest, but portable one, and very expensive, of course. We are also involved in the drive complementary together with University of Sussex and University of National Physical Laboratory. I have European collaboration as well, but in quantum itself is concept of microwave. So, where the fiber laser can be replaced literally by microcomb disc, and then you can generate a comb structure, and then it could be driven, let us say, by a diode. For instance, today of course, it is let us say carbon dioxide laser, which is massive, but if you can replace it with a, for instance, VCSEL laser and then integrate it with the microcomb, then things which are, let us say, require this, you can start to think of like this side. So, that is also happening. Of course, it is a very kind of, at least what we have taken is more holistic approach, which are, that is where it is an ecosystem that has been tried to be set up, rather than just one looking at just one aspect. But this is more what I am leading directly in my group. Part of the work, as I said, I have not sought so much physics, but more innovation side of it. But I have collaboration with other aspects, as I said, microcomb, VCSEL lasers. In fact, this month, early this month, one laser will be tested in my lab for VCSEL lasers for these purposes. So, it is a kind of a journey, it is a, that it is there. Yes, please.
So you said there isn't any electronics that can measure all the vibrations from the ion because they're so rapid.
Yes, laser I said, not ion.
So how exactly are you using to
So, this frequency comb, what happens is, if you have these frequency comb, the way they work, they are mode lock pulse laser. So you have a mode lock pulse laser, and if you take a Fourier transform of a pulse laser in time, then you have Fourier transform, then you have really comb structure, like you have equally spaced spikes, and these equally spaced spikes, the spacing between them now in frequency is really, if you have a cavity and the light is going back and forth, which is called repetition rate, it is typically of the order of 100 megahertz. And then you can break your, let us say, in principle, your optical signal. What you can do is you have like millions of these combs, lines, that is why it is called comb, and then if you beat your laser against one of them, then your laser beat frequency is going to be between half of your repetition rate. It is 100 megahertz, then it is 50 megahertz, for instance, and then that is how you have come down from 10 to the power 14, 10 to the power 15 to, let us say, 50 megahertz automatically. Then of course, you can take other harmonics, amplify them, and you can derive 10 megahertz out of it, 100 megahertz, 1 gigahertz, whatever you like. And because this process is quite phase coherent, then it is actually phase coherent translation of stability into your application domain that you are interested in. That is how it happens. Yes?
When you use this strontium oxide or the strontium, so this oxygen can degrade your entire vacuum system because you are using this oxide in the science chamber. So how do you handle it?
So, yes, when you have vapors, of course, it does put a pressure on your evacuating system, which means your pump. But if you can make it like, the idea here what we have tried is, you shine your laser light, irradiate it for a very short time, very, very short time, of the order of like millisecond. Then you get, and if it is close enough to your trapping region, you just, as I said, most of the fraction which is generated can be trapped, it is trappable because of the distribution itself, and then you capture it and you switch it off very quickly. So, yes. No, oxygen, it goes somewhere and just, does it becomes form a background or form some other molecule, because the number is so small, it does not practically really matter so much, and so you can maintain the pressure with reasonably good speed vacuum pumps which are already available, that is what I mean. So, instead of having more pumps, at least you have reduced things to the same chamber which matters to you. So, this is one aspect. Of course, there could be other innovation ways one could think of, but this is what we have got experience with, and it seems to have worked. Okay, thank you.
I'd like
You can take this if you like.
yes, I'd like to call our CEO,
Oh,
Dr. Sangeeta Mani, to felicitate.
All right. So thank you so much.
Oh, thank you.
Thank you.
Thank you.
On behalf of IHub Quantum Technology Foundation, I would
Can I
like
just
to
take it? Yes, thank you. Thank you.
thank Dr. Singh and everyone here. Thank you so much. This is the first session of our FriQuant seminar series. We will try to have sessions every Friday, although you all are going to be starting with exams soon, which is why we might go on a hybrid or an online mode. But we will try to get you all more sessions on quantum technologies, innovations, and entrepreneurship. So thank you again, and there's tea outside, so you can have conversations over tea.
Yeah, thank you.
Thank you.
Thank you.